Good morning, friends. Time to begin the class. Okay, important announcement. No call 202 exam will be held in the minor exam slot. So probably that's a good news for you. All right. And I hope you remember that tomorrow in the, day after tomorrow in the morning, we have our first quiz. Okay, so quick recap of what we did last time, and let's just quickly finish this off. So we defined the notion of an Euler walk and an Euler tour. So it's a walk or a closed walk which covers all the essentially. Okay, and then in the last class we determined the conditions under which a graph has an Euler tour, right? So we said that the graph must have exactly one non-empty connected component, and everything else can be isolated vertices. And moreover, every vertex has even degree. And remember, this was a necessary and a sufficient condition, right? So we did the proof both ways. Well, one way was easy, so we just stated it as an observation, and the other way was theorem. Okay, so now question which I'll leave for you to think and which I've also added to the tutorial is the following. When does a graph G have an Euler walk? Okay, right? So an Euler tour is obviously an Euler walk by definition. So therefore, if the graph satisfies this condition, right, that it has exactly one non-empty connected component and every vertex has even degree, then of course it has an Euler walk. But then what is the exact necessary and sufficient condition, right? So that is what you need to determine and prove. Okay, so let us leave this at this point of time and start something new, although we'll still be in graph theory, right? So the problem that I want to discuss is something you have seen earlier in the last Con 101 lecture, and it was discussed by Amit sir. What was the problem? Well, he discussed several graph problems, but then the one important problem which we are going to discuss today is the following, right? So let me just copy this diagram. Right, so does this diagram remind you of that problem? What problem I am referring to? Any guess?
The room allocation.
Absolutely, yes. Okay, so let's say you have the IITD hostels containing several rooms. So for now, I've just taken 5 rooms over here, and yes, Abhinav, yes, you are right. And let's pick some 5 random students from the class. Let's say Aman. Isha. Ushagra, let's say. Chalo, Rajat. And Ria. Okay, so each student has indicated his or her preference for the set of rooms. So basically, it's not really a preference, it's a subset of rooms that they are willing to occupy. Okay, right. So let me change the color of this diagram. Yeah, give me a second. Okay, so all edges are green. Cool. So for example, Aman has said he is willing to occupy room number 1, 2, and 4, and nothing else. And now the problem is the following. Can you assign, right? So let's state, so let's say you have n students, n hostel rooms. Each student indicates or rather chooses a subset of rooms they are willing to occupy. And then the problem is, right? So there are several problems. Firstly, can you assign rooms to all students? Secondly, if you cannot assign rooms to all students, what is the maximum number of students that you can assign rooms to, right? So every student has to be assigned a room which he or she is willing to occupy. Okay. And third question is, suppose it is not possible it is just not possible to assign rooms to all students. Okay. Then what do we do, right? So we might want to ask some students to kind of expand their set of chosen rooms. Okay. That is one possibility. Or we might want to improve the quality of rooms so that more students prefer them. But which rooms or which students? Okay, can we systematically determine that? Okay, so that is what we are going to study in the this class and the next class probably. So the question is, can we assign a room to every student? Question number 2, if not, what is the max number of students that can be assigned rooms? And 3, right? So yeah, so the third is a little kind of vague question, so we'll address in the next class, certainly not today, right? So which students should we request to expand their choice or which rooms should we renovate so that more students prefer them, more students like them, right? So this is a bit vague, so we'll do that in the next class. Okay, so this is what we are going to look at in the today's lecture and the next lecture. But the more fundamental question we want to ask is, let's say I give you a graph, right? So this what you can see over here is a graph. Okay, I give you some arbitrary graph and I ask the very basic question: does this graph actually represent this kind of a situation where you have students and rooms, and students have given preferences for subsets of rooms? Okay, so is the question clear, right? So I'm giving you a graph and I'm asking the very basic question: can you identify the student vertices and the room vertices in this graph in some sense? I mean, obviously you cannot completely identify. I mean, I could have very well said that, okay, given just this graph, I could have very well said that the vertices on the right hand side are the student vertices and the vertices on the left hand side are the room vertices. Fine, right? So as long as we are able to label vertices as a student vertex and a room vertex so that every student is connected to a subset of rooms, that's fine, right? But given a graph, is that even possible? That is the question we are trying to ask. Okay, so can somebody give me an easy example for which this is just not possible? This identifying a vertex as a student vertex or a room vertex, right? So what I'm asking is, yeah, yes.
A triangle.
Triangle, absolutely, good, right? So if your graph is a triangle, right? So you just can't determine. It's just not possible to label these vertices as student vertices and room vertices, so that student is right. So all the neighbors of a student are room vertices, and all the neighbors of a room vertex are student vertices. That's just not possible over here. Okay, so
But then shouldn't there be 2n vertices, like according to the question?
according to which question? One of these questions you are talking about?
Like you said, n students and n hostels, so both should be equal, right? That
Oh,
way.
fine. Yeah, I didn't want to make that. Acha, so fine. Let's make it M hostel rooms. Okay, let's consider the more general problem. N need not be equal to M, although it is in this diagram.
Okay,
Okay,
okay. Yes.
yeah, M hostel rooms. So let us give such kind of graph some name. Okay, which kind of represent this situation, right? So definition. A graph G equal to VE is called bipartite, right? So bi refers to two, partite refers to parts, but what does that exactly mean? If its vertex set can be partitioned into two sets V0 V1. So what does that mean? Partition a set into two sets. Mathematically, what does that mean? Mathematically, what does that mean? It means V should be equal to V1 union V2, and the intersection of V1 and V2 should be empty, right? So we call the graph bipartite if its vertex set can be partitioned into two sets V1, V0, V1. Oh, sorry, V0 and V1, no. Such that every edge has one endpoint in V0 and one endpoint in V1. Right? So basically these V0 and V1 are what I'm referring as student vertices, the set of student vertices and the set of room vertices. Okay, although they can be interchanged, that's fine. Okay, any question as far as this definition is concerned? Okay, so that seems clear. Right, and now the question we are trying to ask is what condition should, right, so let me just write down this big question. What condition should a graph satisfy in order to be bipartite? Right? So as someone already said, the triangle graph is not a bipartite graph. Quick question. Let's say Kushagra, could you tell me, is it possible that a bipartite graph can contain the triangle graph? Probably I'm asking a quite trivial question.
Mm, I'm not sure, sir. I don't think so.
Right? So as soon as you see a triangle in a graph, you can immediately conclude that it's not a bipartite graph. Why? Because you just focus on the triangle and ask how do you split the vertices of the triangle into V0 and V1? It's just not possible, right? So because by pigeonhole principle, two of them are going to land up in the same set, and then you have an edge between them, which is not allowed in the definition of a bipartite graph. So what does the definition say? The definition says that every edge must have an endpoint on one side and must have the other endpoint on the other side. Okay, is this point clear? So for example, right, so observation, bipartite graph cannot have a triangle as its subgraph. Okay, so raise your hand if this observation itself is not clear. Let's see whether people are with me. Raise your hand if this observation is not clear. Okay, fine. So yes, Arin. Is this not clear, Arin?
Why, I want to ask, why is a triangle not a bipartite graph?
Why is it?
Yeah, I number the vertices as A, B, C. I say
Okay.
one set as A and B and set two as C. So I have divided the
This
set
is your
into two
V0.
subsets.
This is your V0, let's say, and this is your V1. Is that what you're saying? Right? But you have
Yes.
edges between every pair, no?
Okay, so sir, there should be there. I mean, there must be a subgraph between the corresponding
Sorry?
subsets of vertex. So sir, what is the exact condition of bipartite graph? Sir,
Yeah,
because
exactly.
in here
Exactly
we have
as it is written. You should be able to split V into two parts so that every edge of the graph has one endpoint here and the other endpoint there.
okay, sir. Okay, got it.
Every edge. Okay?
Okay.
Yeah. So anybody else? Okay, cool. Right. So why? Because let me repeat the argument quickly. By pigeonhole principle, no matter how you split the vertex set, if you have a triangle in your graph, two vertices of the triangle are going into the same side, right? Either both in V0 or both in V1, and then you have an edge between them, which is not allowed in a bipartite graph. Right. So therefore, any graph which has a triangle as its subgraph cannot be bipartite. What else cannot appear as a subgraph of a bipartite graph?
Any regular polygon, any polygon.
Any polygon?
Yes, sir. Any polygon.
What about a square?
So square also cannot appear because
Sir, odd
it,
length cycles.
no. This also is not possible because in any subgraph we'll have at least two vertices of
Sure.
we'll have at least two
The
vertices
square
and
can.
So then I can make this as my V0 and the remaining vertices as my V1, no?
okay, got it.
Right? So somebody said odd length cycle. Who was that?
Sir, I said.
Who is this? Chinmay, is it? Okay.
Yes, sir, sorry.
Okay. Okay, Chinmay. Yeah. Yeah. Can you quickly justify that? You're right, but quickly for the benefit of the class, could you
So
please?
like algorithmically, there if we start like if we just arbitrarily give one vertex sum like 0 or 1, then it is bound that at the end the two vertices will like we can I think use pigeonhole principle again also like if you assume there are two k plus 1 edges, then there will be at least k plus 1 vertices having the same color. I think that is not possible.
Yeah, you have the right idea. Yes, absolutely. So let me state that as a claim, or maybe another observation. Okay. A bipartite graph cannot have an odd length cycle, right? And the reasoning is, okay, let's go to the, in fact, let's copy this onto the next slide and quickly write down the proof. Okay. Or rather, let's make this into a claim maybe. Yeah. Okay, so what is the proof? Let V0, V1 through Vm, m minus 1, let's say V0 be an odd length cycle right? So then what happens? That is m odd right? So then the argument is as follows. So suppose, so without loss of generality, let's say little v0 is in the v0 side. So then that implies then v1 must be in the capital V1 side, V2 must be again in V0 and so on. V3 must be in V1, right? Because every consecutive pair of vertices is connected by an edge, right? So that implies where should Vm minus 1 lie? So where Vm minus 1 should also lie in V0. Right, but then this Vm minus 1 V0 is an edge between two vertices in V0, right? So that's not allowed. Okay, so can I slightly make a more general statement? A bipartite graph cannot have an odd length. Can I replace this cycle by it cannot have an odd length closed walk? Is it okay if I make this replacement? I'm making a more general statement, right? Every cycle is a closed walk. So I'm saying the bipartite graph cannot just have an odd length cycle. It cannot even have an odd length closed walk. How many of you agree with this statement? Raise your hand if you agree with this statement. Okay, quite a few people agree with this statement. Cool. Tanmay, do you want to quickly say why?
Sir, I guess the same reason
Exactly.
as which you have explained here. Like if
Absolutely.
V0.
Absolutely. Yes, you're right. You're right, Tanmay. Yes, absolutely. So here I have nowhere used the fact that this is a cycle and not an arbitrary closed walk, right? So, right, I can just make a replacement over here. Let V0 through Vm minus 1 V0 be an odd length closed walk. And then everything goes through. Okay, so cool. So bipartite graph cannot have an odd length cycle. Bipartite graph cannot have an odd length closed walk. Cool. What else is this? Are there other structures that cannot appear in a bipartite graph, or is this all? What do you guys think? Right. So, are there other conditions that a bipartite graph must satisfy, or is it sufficient if I ensure that the graph does not have an odd length cycle? Is that sufficient to ensure that the graph is bipartite? Okay, let's guess. Yeah. Yes, Abhinav.
A one edge, like only one edge is also closed walk, right?
Only one edge is not a closed walk. If you traverse that edge twice, it is a closed walk.
Oh, okay.
Okay. Yeah. What else? Yeah. Any idea? Let's guess. So raise your hand if you think that this is a necessary and sufficient condition, which means that if a graph does not have a closed, if a graph does not have an odd length cycle, then it must be bipartite. How many of you think so? Okay, there are some. Okay, a lot of people, several people. Okay, out of the 56, I think there is around 1/4 of the class, maybe. Yeah. Okay, cool. So yeah, please lower your hands now. So let's see whether there are people who think otherwise. So raise your hand if you think there might exist a bipartite. So there might exist a graph which does not have an odd length cycle, but which is also not bipartite. Tanmay thinks so. Okay. Vedant also thinks so. Oh, he has lowered his hand. So yeah, Tanmay, do you have any intuition of why do you think so?
Sir, no reason, but Just an intuition. Just I think.
Yeah, it doesn't feel complete, is it? The condition doesn't feel good enough, strong enough. Okay, Abhinav. Anybody else? Abhinav, Siddhant, Shubhashish.
Sure, I was having an idea that like suppose we have some A1 to A, like some vertex is only connected to another room. Like some student wants
Hmm.
some room R1 and
Hmm.
only that student wants that R1
Okay.
and no other else. Like this is kind of isolated thing, right?
A disconnected component. Okay, fine.
Yeah,
Right.
yeah,
No problem.
yeah. So I was thinking about these kind of situations might occur there.
So
But
what?
since
What
like
is the problem then?
no, but this is not a closed walk, right? You said.
No, but what I'm asking is, does there exist a graph which does not have a odd length closed walk? It does not have an odd length cycle also, let's say, but it is still not bipartite.
Oh, I'm not very sure, sir.
Acha, okay. Siddhant, Shubhashish, do you want to say something? Viraj? Yeah. Vedant, yes.
Sir, I think as long as there is no cycle, it can always be categorized as a bipartite
Acha, so
graph.
you didn't raise hand for this particular claim as such. Okay, fine. Shrimanti, your hand is up.
Sir, what if we have an isolated vertex, then where would we place it?
You could place it wherever you want, no? That doesn't violate any condition,
Okay.
right? Okay, fine. So yeah, cool. So let's make this statement. Um, let's write down the statement of the theorem. Okay, so I'm going to assume that the graph is connected, and then it will be clear that it's not really a very strong assumption. That is just for in order for us to be able to write a clean proof, right? So okay, so yeah, is somebody saying something? Isha, your hand is up, by the way. Isha, what
Yes,
is
sir. I have a confusion in the
okay?
like the closed walk claim. I understand the cycle one,
Huh,
but like when like I'm trying to construct a counter example for this in which we
huh,
have a square
huh,
and we have another like another point which is outside this and which is connected by just one edge to one of the
huh,
vertices. Yes,
huh,
sir.
huh.
So like as you said that we can traverse a path twice in a closed walk. So
Yeah.
this can form a odd length closed
How?
walk
How?
and so
What is the
sir,
odd length? Let's name this. No, A, B, C, D, E. What is your odd length closed walk over here?
so like we can start from A and then go to B, then to C, then back
Ah,
to B.
from B to C you cannot go, no?
Oh, so sorry, B to E. Sorry, I thought.
B to E, okay.
Yeah, and then back to B, then D, and then C.
Then what?
Okay,
This is not a closed walk,
okay. I mean,
right?
we are traversing an edge twice. So is it?
Which is fine, but you are not returning back to A, no?
Yeah, we can go back to A then
Okay,
after
you
C.
go back to A. So is this a closed, is this an odd length walk? So your length is 1, 2, 3, 4, 5, 6, no?
Yes, sir.
Yeah, Ramanuj?
Sir, I don't think we can make the claim that it is a connected graph. So I think we can just use induction here and say consider one connected component and then
Exactly. So which is why I'm saying let's just focus on connected graphs. If the graph is disconnected, then the argument will apply to every connected component, and the claim will still be true.
okay.
Okay. Yeah. So we'll just prove the claim for connected graphs, right? So I'm sure you're smart. You're all of you are smart enough to extend that claim to disconnected graphs. Okay, Chinmay, your hand is up.
So like I had some idea for the proof of this.
Proof. Okay. First let's write down the statement. Okay. So let G equal to VE be a connect. Okay, let's make it explicit. Connected graph. The following statements are equivalent. Right, what's following statements? 1, G is bipartite. 2, G does not have an odd length cycle, and 3, G does not have an odd length closed walk. Okay, so somebody had an idea of the proof. What was it? First let's identify which claims are trivial.
So like 1 and 2, 1 to 2.
1 implies 2 is easy, no? 1 implies 2, right? So proved earlier. In fact, we also proved 1 implies 3 earlier. Fine, chalo. Yeah. What else? So what idea did you have?
So like either the graph, if it is connected, either it will have an even length cycle or it won't have any cycle. So if it is a tree, like it doesn't have any cycle.
Wait, 1 second. What part are you proving? 2 implies 3, 3 implies 1, 1 implies
2 implies 1.
2 implies 1. Okay. Okay, go on. 2 implies 1. So it does not have an odd length cycle. So then what?
So either it won't have any cycle or an even length cycle, or like multiple even length cycles. So if it does not have any cycle, then it will become a tree.
Yeah.
And in tree, if I just consider any arbitrary vertex, I call it the root. Then from that root, every other vertex has a unique path.
Good.
So if that unique path is odd length, then I will color them different as the root, and if they are even length, I will color them same as the root. So that way we can show, like we can prove that all vertices are colored, and no vertices having belonging to the same edge have the same color.
Okay.
And if it is an even length cycle, again for that even length cycle, we can arbitrarily color the points like all odd numbered points we can call to V0 and other points to V1. Like each edge we just alternatively color every point. Then if we remove the cycle, either the graph will become have several connected components, then we can apply induction. And we can also show that if there was if there was some edge between that even length cycle, like some other vertices of the even length cycle, then if they are the same color, then that means the previous graph had an odd cycle.
Okay, so if I summarize your proof, what I could say is your algorithm is the following: start by coloring some vertex arbitrarily, and then for every neighbor of that vertex give a different color, and then continue this process. The claim is that you will never end up in a situation where one of your neighbor forces one color on you and the other neighbor forces the other color. Right?
Yes.
That seems to be the high level idea behind your argument, right?
Yes, yes.
Okay, good. So that is going to be the high level idea behind our proof also. But for that, in order to write a clean proof and get a concrete argument, we'll take the help of statement number 3. Okay, so what we'll do is 1 implies 2 we have already proved. We'll prove 2 implies 3, and then we'll prove 3 implies 1. Okay. Shrimanti, I think your hand was up, but now it's down. What is it?
Sir, I had thought of an algorithmic proof that we can start from any vertex, and we sort of go on coloring from that vertex till we do not have any more edges, and or if we end up at that vertex, and then like this we mark as visited all those vertices, and then again we continue this for the other vertices, and like this we can have a
then again you're saying that just because you don't have an odd length cycle, you're not going to get stuck where in a situation where one vertex is forced to have red color because of one neighbor and blue color because of another neighbor.
Yes, sir.
Yeah, so that is roughly your argument. Yeah, needs to be made clean, and we'll do that. Okay, Cool. So let's prove 2 implies 3 now. Okay. So the graph does not have an odd length cycle. We want to prove that the graph does not have an odd length closed walk. So let's prove the contrapositive. I.e., if G has an odd length closed walk, then G has odd length cycle. How do you prove this? Raise your hand if you have some idea of how do you prove this. Somil has some idea. Pool. Ramanuj has some idea. Rishabh, yes. Okay. So any one of you, so could you tell if I just allow you to say 3 words and give the proof of this claim in 3 words, what 3 words will you say?
Well ordering principle.
Absolutely, lovely. Okay, do you want to elaborate on that?
So you consider the closed walk with like, minimum number of edges.
The odd length closed walk with the minimum number of edges, and then you claim that it must be a cycle.
Yeah.
Right?
Yep.
Okay, cool. Very nice. Okay. So, right. So now I'm not going into the same well-ordering principle business. I'll not elaborately write that. Okay, look at the set of lengths of all possible odd length closed walk in the graph. By well-ordering principle, it has a minimum element. Pick that minimum element, and because that minimum element is in the set, you must have a closed walk of that length, and blah blah blah. I'm not going to say all that. I'm just going to say consider a closed walk of minimum length. Consider an odd length closed walk of minimum length. Right. So, but remember, implicitly we are using the well ordering principle or the well ordering property of natural numbers over here. Consider an odd length closed walk of minimum length. Right. So remember this by well ordering principle. We claim that this is a cycle.
Sir, excuse me.
Yeah.
Sir, why do you even want to prove 2 implies 3? Because we already have 1 implies 3, and we should prove 3 implies 1. Then we have 1 if and only if 3.
Why do I? Yeah, you're right. Actually, 1 implies 2. We are done, but we want to also prove 2 implies 1. No. How
Okay,
do you
sir.
get 2 implies 1 if you don't prove 2 implies 3?
Okay, sir.
Right. Yeah. Okay. So we claim that this is a cycle. Why is this a cycle? Somebody? Chinmay, yes.
So like if there are two vertices which are same, and if they have odd.
One second, Chinmay, sorry to interrupt you. So let us give this cycle some notation, and then you can use that notation to give your argument. So we claim that the cycle. So suppose the closed walk is V0, V1 to Vm minus 1, V0, where M odd. Yeah, go on, Chinmay.
So if there are two vertices like which are same, and either they will have even number of edges in this walk or odd. So if they are odd, then that is a contradiction. Then that will become the smallest walk. Otherwise, if they are even, we can just remove them and we'll get a smaller odd length walk.
Okay, cool. Awesome. Very nice. Very nice. So, right. So if Vi is equal to Vj for some, suppose Vi is equal to Vj for some ij. Vi equal to Vj for some I less than j. Okay, so then what do you do? If j, okay, I don't need the absolute value, no. If j minus what, j minus I is odd, then what? So then vi plus 1, vj minus 1, vi, right? Vi is same as vj, is a shorter odd length closed walk, right? So this is a contradiction to the minimality of the chosen walk, right? Else what happens? Else, that is j minus I even, then what you could do is, then you could start from vj, let's say vj plus 1, v, right? So somewhere you'll reach, right? So you get the idea, right? I mean, of course, yeah, j and I could possibly be 0, but the idea is you, right? So you go around the same walk, right? So you have vm minus 1, v0, vi minus 1 is a shorter odd length. Okay, I should write a vj over here once again. Shorter odd length closed walk. Right, so basically what we are doing is we are looking at the closed walk, and if some vertex is repeated, then we are splitting it into two walks, right? But because the original walk had an odd length, one of the two walks must have an odd length, right? And then that walk is strictly smaller than the original walk, so that is a contradiction, right? So let me draw a diagram maybe over here. So you have some walk, right? So where some vertex is repeated, let's say. Okay, so you have some walk where at least one vertex is repeated. There could be others which are repeated, but one is good enough for us, right? So now if the original walk had an odd length, then one of these two parts must have an odd length. That's all we are saying. Okay, raise your hand if you are not with me up to this point. Okay, cool, everybody is with me. Right, so that implies, so therefore you have 2 implies 3. If the graph does not have an odd length cycle, then the graph does not have an odd length closed walk. So now how do you prove 3 implies 1? I mean, people did have the right intuition, right? You just go on arbitrarily coloring and then you claim that you will never get stuck. But why will you never get stuck?
So like if we get stuck, then we can say that like let's say there is an edge at which we get stuck. Then when one vertex is the one which we were coloring, and the other one was one which we were trying to color, but it was already colored with the same different color. Like for example, then that means that from that vertex to the other vertex, there must be like that forms an odd length cycle.
So basically, you are trying to say you had a blue vertex, right? You had another. Wait, so what are you trying to say? So you had a blue vertex, let's say you had a red vertex, and then there was a common neighbor of these, right? So this is a common neighbor. Now, because this is blue, you decided to color this red. Now, what is the idea?
So if from this red the circled one, if there was an odd length cycle that had this blue to this red thing as an edge, then that is a contradiction. Otherwise, we can just color this blue and then color all its like neighbors again according to our wish.
All its neighbors again, that's a lot of work. No, why will you ever stop if you go on doing this? Right? You recolor all those things, whatever you wanted to recolor, and then you see a problem somewhere else. Right? Okay. How do you go on? How long do you go on doing this? Yeah, Ramanuj?
So I think what Chinmay wanted to say was like if we ever get a contradiction in which one vertex was say blue first and then you get another neighbor of
like
that,
like
which
sir,
is
this
also
will
blue.
only happen like we started from somewhere, so this circle should be accessible from that point from both the sides, then only we would have come to the situation, and then that cycle must have been an
Circle
odd.
should be accessible from both sides. Okay, idea is clear, but it's not mathematically precise. That is my complaint.
Also, I think Chinmay meant walk because cycle is not necessary here. It should be walk.
Yeah. Again, idea is right in the right direction. Certainly, probably you're almost there. You just need to mathematically put it in the right words. Somil, your hand is up.
So we pick an arbitrary vertex and
Okay.
we partition the vertices into two sets such that two sets V1, V2 such that all the vertices in V1 have odd length walks from the chosen vertex, let's say W, to them,
Okay.
and all the vertices in V2 have even length walks from W to them.
Correct.
Then we
Then
claim
you are
that this
critically
is a partition because if
good.
vertices are in both the sets, then we have a odd length closed walk.
If some vertex is in both sets, then you have an even length walk from W to that vertex, and you also have an odd length walk from W to that vertex. So therefore, the graph contains an odd length closed walk. Lovely. Yes, very nice. Very nice. Rishabh?
I was thinking of inducting on the vertices, and you add that, like, you add a similar extra claim as Somil did, that if two vertices are in like have different colors, there's an odd length walk between them. So
Okay, I see.
then you
So
join them. Yeah,
I think
you
you're on
get
similar lines. You're on similar lines. Okay, cool. So let's, so I also had exactly the same idea which Somil had in his mind. So let's just do that. So what do we want to prove? We want to prove 3 implies 1, no? Right. So now let's define. Okay. So first of all, okay, VE is a connected graph. Okay, obviously there is nothing to prove if the graph itself is empty, right? The vertex set is just one vertex or 0 vertices, there is nothing to prove. So let's assume that V is non-empty, right? So if V is empty, then nothing to prove. Right, this is a corner non-interesting corner piece. So suppose nothing. What's happening? Nothing to prove. So assume V is not empty. Okay, so let R be a vertex. Right, so we'll define two sets now. Let V0 be the set of all V in V. Right, so remember the graph is connected, so there exists at least one walk from R to every vertex in the graph. Right, so V0 is the set of all vertices such that there exists an even length walk from R to V. We use U maybe because it might be hard to distinguish between the uppercase V and the lowercase v. Okay, so it's the set of vertices U such that there is an even length walk from R to U, and similarly V1 is the set of vertices U such that there exists an odd length walk from R to U. Okay, So sorry to go back to an earlier definition. I forgot to say that if a graph is bipartite, then such a partition V01 is called a bipartition of G. Right. So let me just add it over here, right, so that we can conveniently use that term in our proof. V0 V1, the pair V0 V1 is called a bipartition of G. Okay. So now coming back to the proof, what do we want to prove? We want to prove that V01 V1 is a bipartition of G. Right. So we claim that V0 V1 is a bipartition of G. So what do we need to prove? Firstly, we need to prove that it's a partition in the first place, right? Which means every vertex belongs to exactly one of V0 and V1. And secondly, you need to prove that it's a bipartition, which means every edge has one endpoint in V0 and the other endpoint in V1. Right. So why does every vertex lie in why does every vertex lie in at least one of V0 or V1? Somebody quickly.
Because the graph is connected.
Chinmay, yes, graph is connected, right? So since the graph is connected, V0 union V1 is equal to V. Yes, Isha?
Could I have a slightly different proof to this? Maybe I'll tell that after this one.
Okay, fine. So, but remember to raise your hand, otherwise I'll easily forget that you are trying to say something. Okay. Okay, so the union of V0 and V1 is equal to V. V0 intersection V1 is equal to empty set, because if not, right, because if some X belongs to V0 intersection V1, right, what does it mean? There exists an even length even length R2X walk and also an odd length R2X walk. Therefore, there exists an odd length closed walk. Right, so here is where this closed walk is really helping us, right? I mean, if we just assume that the graph does not have an odd length cycle, here we would have landed up in a difficulty, right? So which is why we needed the 2 implies 3 claim. Okay, so there exists an odd length closed walk, so which is why V0 intersection V1 is empty. Yeah, so now what? Now suppose UV is an edge. Okay, if what? If U belongs to V0, then what? So then there exists an even length R2U walk. Okay, append V to that walk. Right, so there is an even length R2U walk. Just append V to that walk. Why? Because you can do that because U and V are adjacent, right? So append V to that walk to get an odd length R2V walk, right? So therefore V belongs to V1, right? And then similar proof is if U belongs to V1. Right, I'm not going to write that once again. Right, Isha, you had some different ideas.
Yes, sir. So maybe we can prove this by contrapositive. That is, we can say that like if G is not bipartite, then G must have an odd length closed walk.
Okay. How do you do that?
So if G is not bipartite, then there must be at least one like edge. If we try to make a bipartite, like we run the bipartite algorithm on this, then there must
What
be
is the
at least
bipartite algorithm? What is the bipartite algorithm? We
like
didn't.
we start coloring from one of the vertices and like color it all around.
You'll have to properly define that algorithm first, and then you're saying that okay, if you run it, then what happens?
So then there must be at least like when we are partitioning into two sets, there must be at least one edge in the same set, like in the same partition.
But then first of all, you will have to prove that whenever the graph is bipartite, your algorithm actually outputs a correct bipartition.
Yes.
And so that is something you'll have to prove, right? What if the graph is bipartite, but your algorithm does some wrong choice, which is why it's not able to construct a bipartition? Then what? Okay. Yeah, Rishabh.
I also had another idea.
Okay.
So first you prove it for a tree. That is easier because there's no issue with walk and all. So now you take a spanning tree of the graph.
Okay.
You color it because you have proved it for a tree.
Okay.
And then because all cycles are even, any edge which might cause an issue is from your from one vertex to some other vertex on the tree, and like they will have different distances. Their parity of distance would be odd if they have to be sorry, the parity of distance will be even if they have to wait.
Odd, no?
Oh yeah, it'd be odd. So you end up with
wait. Let me parse that argument. Give me a minute. So you are coloring, okay, you are just considering a spanning tree, and on that basis, you are assigning the vertices on either side of the bipartition. Fine. And now you start looking at the non-tree edges. And now you want to claim that every non-tree edge has one endpoint in one set and the other endpoint in the other set. Otherwise, what will happen?
if they do, then we'll have an issue. Right. Sorry. Yeah, my bad.
Yeah. So if some edge has both its endpoints on one side, then you want to claim that it will form some odd length cycle. That looks promising, except that now you'll have to prove. Wait. So how did you construct the bipartition? You looked at, right? So it needs some argument, right? So
you can like either try to induct using the like subtree property that once you remove a edge, you can
so
find
I think the
trees.
easiest way.
You could like just take distances and based on the parity give them colors. This is nice because it also helps with the next argument.
Okay. So I think what you are saying is look at pick one arbitrary vertex and call it the root, and then construct one spanning tree, and then based on the spanning tree, you look at the distance of the root from any vertex, and depending on the parity of the distance, you will color the vertex. Now, the one thing that you'll need to prove is that if two vertices have the same color, then the unique path between them in the tree has even length, and otherwise it has odd length.
Yes.
Right. So that needs
hard because there's only one edge and there's only one path.
There's only one path, but yeah, exactly. So that is something which will take some of your effort. Somaditya?
Yes, sir. I had an idea of how we could do 2 to 1.
What 2 to 1?
Sir, how we could prove
2 to 1. Acha. Okay.
Using just the cycle claim. So if we partition the so just like the other ideas, if we select one vertex and then we partition all other vertices based on the parity of the shortest path length from that chosen vertex
to the root.
Yes, for the chosen vertex, the parity of the path from the chosen vertex to any vertex.
Shortest path. Okay.
Okay. So then suppose two vertices are adjacent and both have the same parity. Suppose both have even shortest paths.
Okay.
So then if we consider the paths, the last common point of those paths.
Last common point of the both paths. Cool. Okay.
Which might be the root itself.
Okay.
Sir, then from the root to that last point, both paths will have the same length.
Wait. Wait, hold on. I don't think I agree with this. Let's try to draw some diagram, right? So you are considering one possible one R, and then from this R you are looking at the shortest path to every vertex U, and then depending on the parity of that path, you will color the vertex U, vertex red or blue. Let's say. So let's say you have a red vertex U, and you have another red vertex V, and then there is some path from R to U, and then there is another path from R to V, and both of these are the respective shortest paths. Then what?
So the last common point, which
Common point.
yes, you can mark this, sir. Then I claim that from R to this point, both the paths have the subpaths have the same length.
Same length. Why?
Sir, if not, then the other could be made shorter, I think.
No, not at all. Let's say this is your X, this is your U, and this V. Right?
Yes,
It
sir,
not have the same length.
No, sir, from the R to X. I'm saying R to X.
Oh, R2X. I see. Yes, yeah. So you're using the fact that every subpath of a shortest path must also be a shortest path between the respective endpoints. Yes. Cool. Yes.
So then just connect U to V and we get an order length cycle.
Yes, that sounds good. That sounds good to me. Okay, cool. Somaditya, your hand is still up. Is there anything else?
I was thinking of the previous argument. I think it's the same argument as mine if you consider the BFS spanning tree.
BFS spanning tree.
Because if you specifically consider that, then you'll get this shortest path argument.
What is the BFS spanning tree? We haven't defined it in class. Not
Ah,
everybody.
Yes, sir. I'm just making note.
Okay, fine. All right. So we know what kind of things don't appear in a bipartite graph. So how do you algorithmically determine whether a graph is bipartite? Let's leave that for your call 106/call 331, right? So when you do graph algorithms over there, hopefully this will be taken. Okay. All right. So now let's come back to the original problem. Okay, let's copy this diagram. Okay, what is wrong with this? Right, and then who are the students? I forgot the names now. Aman, Isha, Kushagra, Rajat, and Riya. Okay, so here is the situation, right? So let's get back to the problem, right? So each of these students has given a subset of rooms as their preference, right? That is the subset of rooms which they are willing to occupy. And now we want to firstly, right? So let's go back to the two of the three questions. Can we assign a room to every student? And let's just focus on the second question, right? So what is the maximum number of students which can be assigned rooms? Okay, so okay, let's copy this. right? So forget the if not part, irrespective of whether everybody can be assigned or not. My question still remains the same. What is the maximum number of students that can be assigned rooms? Right, so meanwhile, you can just stare at this diagram and figure out what is the maximum number of students. Yeah, anybody? Yeah, Vedant?
So in this case, all can be assigned. All 5
Okay, can you
people
give me
can.
an assignment? Can you give me an assignment?
So Ria is assigned to room 3.
Achha, Ria is assigned to room 3.
Then Isha is assigned to room 5.
Okay.
Rajat is assigned to room 2.
Okay.
And who is left now?
Aman and Kushagra.
Kushagra can be assigned to R2 and Aman to R1.
Sorry,
No,
say that
but
again.
Rajat already has R2.
Yeah, so Kushagra could be given R4 instead.
Kushagra should be given R2 and Rajat what?
No, sir. Kushagra R4 and Aman is
R4.
R1.
Achha,
Yeah.
I didn't hear you properly.
Yes.
R4 and Aman gets what? What is the remaining room? R1, is it?
R1, yeah.
R1. Let's verify. Aman gets R1, cool. Ria gets R3, ठीक है. Rajat gets R2, okay. Isha gets R5, ठीक है. Kushagra gets R4. Yeah, that sounds good to me. Okay. How do you systematically find this assignment? Right, that is right. So here you just stare at the diagram, but that's not what a computer is able to do, right? If you give the computer a bipartite graph and ask, can I have an assignment of rooms to students? It's definitely not going to stare at the graph and try to find something, right? How can you systematically and efficiently find the rooms, right? So let me explain the idea behind this algorithm or whatever before I make the formal definitions. Okay, so let's say, right, so the idea is the following. You start with the empty assignment, nobody is assigned any room, and then in every iteration you assign one more student a room. You successively improve the set of students who have been given rooms, and once you find that you cannot improve on this, you just stop, right? So how do you do this improvement? So let's say at this point of time, let's leave this aside. Okay, there is something on chat probably. Backtracking, Shrimanti, the problem is backtracking is really a brute force approach and it could take you a hell lot of time, right? Backtracking is usually not a recommended approach because it's going to take, it's usually runs in exponential time and that's not what we are looking for. We are looking for much more efficient algorithms. Yeah, Shrimanti, yes, but you'll get to a right solution. I mean, well, Shrimanti, in some sense, backtracking is same as trying out all possible assignments and then verifying whether each assignment is a feasible assignment or not. Chinmay, yes?
So like you said now.
Yes, go on, Shrimanti.
So like you said now that in every iteration we try assigning one more student, but if that fails, then we go back. Like
No, I never said that. I never said that. So in every iteration, there are two possibilities. Either you are able to assign a room to one more student, possibly after some reassignment, or you will figure out that I just cannot assign any room. I just cannot assign more students rooms, right? So this is the best possible size of, this is the maximum number of students that I can assign room to. Okay, so one of these is going to happen in every iteration. Chinmay?
So like I was thinking if we could think in terms of the rooms, like we can sort the rooms in terms of the number of edges they have.
Okay.
Like the ones having 0 will not be assigned to anyone.
Yeah.
And then
Good.
ones having 1, we can just assign it to that student and remove all other edges that student has. Then we can like
Good.
keep on doing this. I think it will be optimal.
What if you land up? Acha, okay.
We can just assign like for example, when one rooms with 1 edges are finished, then all other rooms will have 2 edges, or maybe they still have 1 because
exactly. Now you have a choice. What do you do?
So when we have 2, we can assign it to anyone. Then we can prove like if from the optimal ordering, we can come back to our ordering, something of that sort.
Something of that sort. That's weak. Okay. Can you do this at that? I'm not entirely sure. So I'm really worried. So this, yeah, so degree 1 and degree 0 cases, I'm not at all worried about, as you said, right? So what if everybody has some nice, let's say if each vertex has some degree at least 100, what do you do? It's not clear, right? And then it might happen that, okay, you make some arbitrary choice and then that kind of completely spoils your effort, right? Had you not made that choice, you could have assigned rooms to all students, but because you made this choice, you'll end up in a problem. That is entirely possible. That is my worry, basically. Although I don't have a immediate counter example for that. Viraj?
So like as Chinmay suggested, like we can also keep like how many like rooms are remaining, how many choices of rooms are remaining for the students as well, and then we can connect the, like if you have two choices, like if you have two students who for one room, then we can assign it to the one who has lower number of remaining choices, something like that maybe.
Lower number of remaining choices. Wait, two students for one room, and then you will assign it to somebody who has a lower number of remaining choices. So let's see, right? So you have this one room. You have two students who are interested in this one room. This person has a lower number of choices. So you are planning to assign this person this room, right? So this person just has two choices. And then this person has, let's say, 3 choices. So where could the problem occur? Yeah, the problem could occur here itself, right? Because I mean, yeah, so somebody could be interested in this room. I don't know, right? So because this student has a lower number of choices, you assign this, right? So this is the room of conflict between these two. And because the second student has a lower number of choices, you assign this room to this student. Now the problem is that this student doesn't get a room, or I mean, yeah, so there could be other students, right, who are kind of interested in these rooms also, right? And they could have more choices, right? So it's not clear, right?
So, but then when, like, if the other students have other choices, like when we come to that room, then we would assign that. Then this one would get it, right? The one we left out here. If the other ones have
let's call these students something. No, student number 1, 2, 3, 4. Yeah. So now, what are you trying to say? Room number 1, 2, 3. Let's say 4.
So like we left out student 3 here, but then like you're saying that 3 will get left out later when we come to the other rooms as well.
Yeah, I mean, basically,
I cannot argue rigorously that this will be the optimal. That is.
Yeah, so what I'm trying to say is, if for room 3 you give a preference for student number 4, because student 3 has a larger choice, the problem is the following, right? So once you assign room 3 to student 4, it's just impossible to assign rooms to all 3 of students 1, 2, and 3. Whereas what you could have done is assign student 1 room 1, student 2 room 2, student 3 room 3, and student 4 room 4.
So, but we'll go like as Chinmay said, right? That we'll go according to the number of students interested in a room as well. So, like 4 we will treat first because it only has one student who can choose.
You could have other students interested in 4 also. Why not? You could have several other students interested in 4, but still the problem is going to persist. Okay. Right. So, yeah. Okay. Good. Okay. So let's get back to the diagram. Okay. So the idea is to successively improve your room assignment. So let's say that the red edges represent room assignments, which means Aman is in room 2, Isha is in room 4, and Riya is in room 3. How will you improve this? You might, if you want, you might ask students to, okay, you might want to offer a different room to a student who has already been offered a room. That is allowed, let's say. Rishabh?
So you consider the path R1 to Aman, to R4 to Isha to R5.
One sec. R1 to Aman to R what? 4.
Yeah.
R4 and then what?
Isha.
Isha.
And then R5.
R5. Wait. R1 Aman, R4 Isha, R5, and then what do you do with this?
Then you like flip all the edges.
If you flip all the edges, so R1 to Aman is...
Sorry, R2. It starts with R2. Not
Start
R1.
with what?
R2.
R2.
Right. Wait, I think I misread a bit. Yeah, sorry. This won't work.
You are on the right track, but yes.
Yeah.
So here, red are those which we cannot assign, right?
Sorry?
So what do the red edges represent?
So red is the current assignment. Red means Aman is sitting with his luggage in room 2, Isha is in room 4, and Ria is in room 3.
Okay.
They have not opened their luggage, so you can comfortably tell them to. You can comfortably request them to. You can comfortably say that. Could you please shift from this room to that room? That is.
Okay, so instead take Kushagra R2 Aman.
Okay. Kushagra R2 Aman.
Then R4.
Then R4. Good.
Isha and R5.
Isha and R5.
Yeah.
Let's see. Kushagra R2 Aman. R4 Isha R5. And then what do you mean by this path exactly?
So now you. So their alternating edges are part of the matching. So you flip the edges which are part of the matching and which are not.
Okay, but what exactly are you doing over here by this path?
So you are basically increasing the number of students which have a room by 1.
Achha, so you're trying to say that, okay, you'll tell Kushagra to go into room 2, but you'll find Aman over there. So you'll request Aman to occupy room 4, but you find Isha over there. So you request Isha to occupy room number 5.
Yeah.
Achha, cool. Ramanuj?
So I think generally this is starting with a person who hasn't been assigned a room, and then going a path and ending to a room which hasn't been assigned a person.
Achha, cool. Yes, you're right. So that is the idea. Precisely that is the idea. Absolutely. Very nice. Very nice. Okay. So, right. So in this diagram, so current assignment. Current assignment as shown in the diagram is Aman R2, Isha R4, and Ria R3. So how do you improve this? Improvement is what? So Kushagra occupies R2, Aman shifts from what? R2 to R4. Then what? Isha shifts R4 to R5. Yeah, very nice. Very nice. So this is precisely the idea behind the algorithm. Okay, and then but of course we need to claim that if your room assignment is not optimal, if it is possible to assign, right? So what are we doing? We are assigning one more person a room, right? But what if right now you have assigned some 100 students a room, and the best possible way to assign rooms is to assign rooms to some completely different set of 101 students, right? So by this process you are never going to get that, right? So this needs a proof, right? So if you want to claim that this gives you the best possible assignment of rooms to students, that needs a proof. Every time it is improving, true, but why will it get to the best possible assignment? Is the point clear, Chinmay? Yes.
So, could you please repeat the algorithm? What are we doing? I got lost.
So I'm going to precisely state it right now. I mean, as far as this example is concerned, is everything okay? Right? I have not stated the general algorithm. I'll do that maybe in the next class. But as far as this example is concerned, is this policy okay?
Sir, yes, could you explain it again for this example?
Yeah, for this example, we see that right. So I don't know. I forget the name of the person. The idea that person had was to figure out a path in which alternating edges are green and the remaining are red. Right. So he figured out this path. Kushagra to R2 is a green edge, R2 to Aman is red, Aman to R4 is green, R4 to Ria is red, and R4 to Isha is red, and Isha to R5 is green. And then
so it's a way like starting from some person having a green edge, and then you're like keeping shifting on till we
Exactly. So you make that green edge into a red edge, you make the next red edge into a green edge, and so on. Right. So my question is the following. Suppose you have some assignment, you have some 100 students and you have assigned them rooms right now. Right. So some assignment you have made. Right. But in the optimal solution, the optimal solution is of the following form. Right. So there is a completely different set of 101 students which are assigned some rooms. Right. What you're doing over here is in every iteration you are assigning one more. Okay, so people who had a room are still going to have some room. You're not throwing them out. Right. So my question is, what if initially you made a wrong choice of assigning these 100 people a room, and then it's just not possible to improve this assignment? Can you land up in such kind of a situation? Right. So that is what we need to investigate if we are trying to analyze this algorithm. Okay, so we have like 8 minutes left. So let me just make some definitions let me make some formal, let me introduce some formal mathematical terms for this, and then we'll look at the algorithm in the next class. Okay, so okay, so definition. Let G equal to VE be a graph, not necessarily a bipartite graph, matching in G is matching M in G is a subset of edges of G such that no two edges in M share an endpoint. Right. So what we are looking for in this problem is really a matching between the students and the rooms. Right. So specifically, we are looking at the bipartite case, but the definition is completely valid even if the graph is not bipartite. Okay. So another definition, right? So we want to give a name to this kind of a path, right? Kushagra, R2, Aman, whatever, R4, Ria, R5, right? So remember, these edges were red. R2, Aman, sorry. R2 Aman and R4 Isha were red edges, and the remaining were green edges. The red edges are in the matching, the green edges are not in the matching, right? So another definition. Right, so some parts of this definition are also applicable to non-bipartite graphs, but we'll restrict our attention to bipartite graphs. Let G equal to VE be a bipartite graph and M be a matching in G. Okay, so now we want to define something called an alternating path, alternating cycle, and augmenting path, right? So an alternating path of M respectively alternating cycle of M in G is a path respectively cycle that has alternate edges in M and not in N. Right, so for example over here over here, this is an alternating path. I'm not sure whether we have an alternating cycle over here. Yeah, we don't have an alternating cycle over here, but yeah, we'll take another example in the next class and we'll show an alternating cycle, but I hope you get the idea, right? So yeah, so basically Kushagra and R5, right? So if I were to draw a red edge between Kushagra and R5, then this and append Kushagra over here, that would be an alternating cycle. Okay, right, and now, okay, importantly, an alternating path, alternating cycle, an alternating path is called an augmenting path of M is called an augmenting path of M if what? If right, so the first and the last edges of this path are not in M. Right, so what are we saying? It's an alternating path, which means the edges are alternately in M, out of M, in M, out of M, and so on. But more importantly, we are saying the first edge and the last edge are not in M, which means that therefore every augmenting path has an odd length. Has odd length. Right, so this was an augmenting path. Kushagra, R2, Aman, R4, Isha, R5. Right, first edge and the last edge are not in M. Right, and then it's an alternating path. And similarly, also every alternating cycle, right, because it's a cycle in the bipartite graph, of course it has even length. Right. Okay, so we'll use right, so we'll use this terminology of matching, alternating paths, cycles, augmenting paths, and so on, to describe an algorithm and prove it indeed finds the maximum. Right, so what are we looking for over here? We are looking for a matching of maximum possible size in a given bipartite graph. We'll prove that the idea which we had of successively improving the matching actually gives us a maximum matching. Okay, so we'll do that in the next class. All right, so that's all for today. We are meeting in the evening for the tutorial. So see you then. Bye bye.
So the announcement you made, that meant that before the minor there is nothing other than quiz 1, right?
Yeah, nothing other than quiz 1.
Sir, around which time after the minor, like 2 to 3 days, or
what?
3 to 4 days? The second quiz.
Second quiz, I didn't make a declaration at all so far. Whenever it is, I'll declare it in one week in advance at least. Whenever it's going to happen. Okay, so don't worry about it. All right, chalo. See you in the evening.